Okay, so I think it's about time that we formally begin talking about the notion of distance between vectors. I've said it a few times in the previous recordings where, like, are we close to this value? What do I mean by close? And that's what we're going to look at today. So this section will be on norm and distance. Very important topic. In fact, one of the most important topics that we'll cover, because it's fundamental to pretty much everything that we're doing. So let's begin with the definition. The Euclidean norm of an n vector x is the square root of the sum of squares of the entries. Using vector notation, this is the square root of x inner product x. And this business over here, this is more advanced notation when you see a little 2 at the bottom, because the Euclidean norm is sometimes referred to as the 2 norm. And that's why there's a little 2 there. But the only norm that we're going to see in this textbook is the 2 norm, the Euclidean norm. So we're just going to write these double brackets or double lines around the vector to indicate the norm. Okay. But there are other norms, and norms are you can think of them as a metric, a way to measure something, measure distance. And there's different ways to measure distance. This just happens to be one of them. Okay, so in particular, like let's kind of focus in by why it would be called the Euclidean norm. Well, suppose we have a norm we have a vector in R2. So, and it's like maybe like here or something. So this is like x1, x2, right? One way of like thinking about distance here is to look at how long that line is. That's one way to look at distance. How long is a line from the origin to that vector? Well, using a right triangle, so here, this is like your x1 right there component, and then here, this is like your x2 component. So this squared plus this squared is equal, so this is like your d, then that distance there is equal to the square root of x1 squared plus x2 squared. And that'll give you the length there, which is the same thing as saying the square root of x inner product x. Okay. So that's the motivation behind this definition for the norm, for the 2 norm. That's why it's called the Euclidean norm. It's equivalent to the Euclidean distance. So, okay, but what are the properties of the norm? Well, we have so non-negativity. And homogeneity is all one, like, together. Spell that. And what this says is basically that the norm of a scalar times a vector is equal to the absolute value of that scalar times the norm of the vector. Okay. And with the two norm, it's not hard to deduce this at all. But this is just a property that you can work out. And we just have non-negativity on its own. So, like that. All norms are greater than or equal to 0. Definiteness. So I usually combine non-negativity and definiteness into one positive definiteness, but your textbook chooses a different route. So all this says is that norm of x equals to 0 if and only if x is the 0 vector. Okay. And then finally, the triangle inequality. And all that states is that the norm of x plus y is at most the norm of x plus the norm of y. And we'll show why that's true in a bit. Okay, so these properties are important to note, to realize when you're deriving properties of algorithms, properties of theorems. It's important to know the rules that are allowed, that are always true. Not rules, the properties that are always true. And I would just have them like on a little note card, maybe, whenever dealing with norms. Okay, so how does the norm play into what we've been doing? How can we use it? Well, we can use the norm, the notation for the norm, to simplify equations that we'll run into. So for example, I'm going to start talking about equations like that. One would be root mean square value. And this will be denoted in this textbook by bold R M S of x. And this is just the norm of x divided by the square root of n. So if it's an n vector, this would be the root mean squared value. Okay, and when you see this the way it's written, it might not look like anything, but if you rewrite, so what is the norm? It's just the square root of x1 squared plus dot dot plus xn squared, and then this is all being divided by root n. Root mean square value is, well, square root down there, square root up there. This is saying the square root of x1 squared plus dot dot plus xn squared all over n. So what is this? This is the mean or average of the squares of the entries of the vector, and then you're taking the square root of it. But this notation will become cumbersome in the future, so you can see how writing out the norm instead of writing all of this will make things shorter. Okay. 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 So a lot of times you will encounter equations that kind of they represent identities or you will encounter inequalities that can be used in proving theorems. And for example, I might show you one simple, so maybe this norm of a sum. Okay, so this is just an example of an identity relating inner products and norms and sums. So suppose I wanted to know, just play around with what this looks like. So this is the norm of the sum all being squared. Well, this is going to be equal to this inner product. Now, I write that down without any hesitation, but I'm almost positive one of you, maybe more of you, don't immediately see that this is equal to that. What is this? This is the addition of all the elements in x and y, right? Pairwise addition. Square root of all those terms being squared, and then you're squaring the outside. Maybe I'll write it over here because I'm going to run out of room over there. So this is the square root, all being square root of what? x1 plus y1 squared plus plus xn plus yn all squared. So this is the same. Square root, the square of the square root, we're just left with this. Anytime you see a sum of squares, you can write that as an inner product. So that's why this is true. And then we know through properties of vectors that we can distribute the inner product across. So this will be x times x plus x inner product y plus y inner product x plus y inner product y. So I'm just like, I'm showing you this just to kind of re-emphasize the rules of the game, how to distribute across. But now I noticed something here. X transpose x, that's just the square root of, well, hold on. That is that, right? X transpose x is the sum of the squares. And if we take the square root and square it, we get that, okay? Just like how I showed that that's the same thing as that, this is the same thing as that. And then here, I can rewrite y inner product x as x inner product y. And when I do that, I get two of these things. So I get 2 x inner product y, because this is the same thing as that. And then here, I get the same thing showing the product of that all squared. Okay. So what this is saying in the end is that if I wanted to have a formula for the norm of the sum, if I take the square root on both sides, I get this. And again, I was just trying to illustrate the rules of the game and deriving new formulas from what you know. This formula here gives you a formula for the sum of that norm. It could be useful at some point, but it just depends, right? Depends on the context. Okay. So now we should probably discuss how the entries of the vector can relate with the norm of the vector, right? So as the entries in the vector get larger, how does that affect the norm of a vector? And we can do that by looking at this Chebyshev inequality. And maybe this inequality will be a better illustration of why knowing how to manipulate these quantities is useful. So maybe suppose x is some n vector, okay? X is some n vector, and k of the elements in X satisfy X by greater than or equal to A, where A is just some positive number. Some positive number. So there's a bunch of elements in X, and k of them are bigger than some number A, some positive number A. So in this case, if k of them are bigger than A, then what we can say is that, so then if we look at the norm squared, right? That's just the sum of the squares of the entries in X, right? Dots, 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 plus same all squared. Okay. But this is going to be greater than or equal to, well, those entries here all squared. Right, so I guess the best way to write it is that somewhere in there, you're going to have those k entries that satisfy this, and the square of those is like taking the square of this, and this is all greater than or equal to the k of them times a squared. Okay, and that should probably, I'll give you a reason, makes sense. K entries in X have xi in absolute value greater than A, implying that xi squared is greater than or equal to A squared. So since there's k of them, the very smallest that this sum could ever possibly be is k times A squared. Since some of them in there satisfy that, k of them, I mean, the very smallest it could be is this. Okay, so dividing by k now, we're going to get information about the entries. Okay, so this here means that that is greater than or equal to this, which means that A squared, or no, I'll say k, I'll divide by A squared. K is less than or equal to norm squared all over A squared. Okay. So you're probably wondering, like, why? Why are we doing this? Well, we're trying, so here in this line right here, we have a lower bound on the norm. This is a number being squared. this number, we were trying to somehow relate it to the entries in the vector. So how big is this number? How small can this number be? Well, it can be no smaller than k times a squared if k of the entries in that vector in absolute value are larger than a. So what happens, like, okay, what happens when a squared is greater than the norm squared? Or maybe I should say this. What happens when a is strictly larger than the norm? Okay. When a is strictly larger than the norm, if we look up here, then, oh, wait a minute. K is less than or equal to that. But if a is strictly larger than the norm, then this is going to be less than 1, right? Which means k is just is the number of entries in the vector that must satisfy this. Which means that if that's strictly less than 1, because this is bigger than that, then k must be equal to 0. So that means that 0 elements of x satisfy x. But a is greater than the norm. So what we just learned, what we just derived, is that no elements of the vector x can be greater than or equal to, or no, strictly greater than the norm itself. That's what we learned. Okay. And I know based off of your previous math courses about calculating things directly, finding numerical values, this might seem different, and it is, because now, as like we're maturing a little bit in our mathematical knowledge, in the mathematical objects that we're encountering, we're using techniques that look drastically different than what you're used to in order to understand more about the objects that we're working on instead of just computing things. Okay. Okay. But if you were to put like a note on it, it would just be what I said. We derived Chebyshev's inequality, which leads to the observation that no elements in the vector can be strictly greater than the norm. 0 elements have that ability. That was the goal. Okay. So now let's move on to distance. So Euclidean distance. Okay, so this is defined as the following. The distance between n vectors a and b is equal to the norm of the difference. Okay. So this is how we define distance in with the two norm, Euclidean norm, between two vectors. Right, so this should be familiar because the two norm in one dimension acts like the absolute value, and the absolute value between two numbers is the distance between them. Okay. So how can we understand this? Well, let's just say, well, let's just do an example with two vectors. Say if A is equal to 1, 3, and B is equal to I don't know, 2, 2, and C is equal to 10, 4. Let's look at how the distance function is going to show these, how these vectors relate. Okay, so this distance between A and B in this case is equal to, so A minus B, so we're looking at the norm of, so 1 minus 2, so minus 1, 3 minus 2, 1. Looking at that. So this is A minus B, A minus B. And what is it equal to? The square root of 1 squared of root 2. So that's the distance between A and B. Let's look at the distance between A and C. So 1 minus 10, and minus 9, and then 3 minus 4, minus 1. So this will be equal to square root of minus 9 squared plus minus 1 squared, which is root 82. Is 2 times 41. You can compare these numbers and see that this is much bigger than that. And that's because if we look at A, so 1, 3, so this would be like A, and then B would be 10, 4, so 1, 2, 3, 4, 5, 10, and then up 4. That would be so C, and B would be 1, 2, and 2. And that would be B. A, B, C, you see that these are closer than these are. Okay. So now this here is really useful, which by the way, this is the square root of A minus B transpose times A minus B, right? Always remember that you can write the two norm in terms of inner products. Okay, so why would this be useful? Well, actually, this here is a good illustration. A and B are similar to each other, but C is far away. Can this somehow like capture similarity between objects, between data? So let's go ahead and look at that. So imagine that you have a bunch of movies, right? You have like movie data. So movie name, maybe IMBD rating, or whatever it is, whatever that rating is. And then you have genre like horror, yes or no, is it a horror? And then maybe like, is it a kid's movie or something like that? And for each movie name, I don't know, name 1, name 2, name 3, name 4, so forth and so on, right? We just have a bunch of movie names. And then we have some rating, however you want to make the numbers, like, I don't know, 9.1, 2.4, 3.6, 5.7, 8.2. And then you have another entry that's like, okay, this was a horror, this was not, 1, 0, 0, 1, 1. Maybe they mix up a little bit, something like that. So now, for each movie name, you have a vector. Now you see that, right? Each name has a corresponding vector of features that go along with it. Okay. And if you think about these vectors existing in space, oh, so these are, luckily I didn't put another one, I can actually draw this. These are three-dimensional vectors. Right? These are vectors in R3. So I'll say that like, this is x1, x2, x3. So hopefully I do this. Okay, so suppose you like maybe maybe you watched this movie and you liked that movie. So this would be the red movie, and you like this one. Oh, so this one's really easy to draw, I think. 8.200. So 1, 2, 3, 4, 5, 7, 8. So this is name 5. So you like that movie, and there's a bunch of movies in the database, and you want to have recommendations for 2 other movies that you might want to watch tonight, based off the fact that you like that movie. Well, we can treat each of these movies as vectors in space. They have 3 entries each, so let's do that. So 5, so I need to. So name 4 maybe would be, so 1, 2, 3, 4, 5, and then over there up 1. So there's that point in space. And these are all vectors, right? These are ordered triples. So this would be like name 4. And then we have name 3, 3.6, and then 0, 1. So 1, 2, 3, 0, and then up 1. This would be like name 3. And then name 2 is 2.401, so it's like there. So name 2. And then name 1 is 9.1 this way, and then here, be like right And that's right there is name 1. Okay. Which are the 2 movies that you would recommend to me if I write name 5? Based off this picture, which movies do you think are closest to this one? That point right there is close to there. So I would say maybe that movie's similar to that one, and the person that liked this one would enjoy that. Also, the next nearest one is probably this one. It's further away, but it seems like that would be something to recommend. Do y'all see that? Maybe that one's too far away. Maybe we would only recommend one movie in the database that was similar to that movie that I like. You see that?
Yeah, that makes sense.
Yeah, well, in that case, isn't like rating the only thing that matters?
Possibly, but I wouldn't say completely. In this example, yes, I think that that's a good analogy, but this is kind of a made-up example I just did. I do notice something else, though. I noticed that these are clustered and these are clustered, right? If we look at like the distance between points, those distances kind of cluster them together. Right? These are all close together using distance. These are all close together using distance. Are these somehow different than those? These movies here, I did this by accident, but I just noticed it. These movies here are not made for kids. You see that over there? And all of these in this cluster are movies that were made for kids. Kids movies, not made for kids. Based off of how close the vectors are of features in space. It's a natural way of clustering data by distance in space. Okay. Any questions on that? Does it make sense that this would be a way to put things into groups? Right. So this is, we're now starting, now that we know how to describe distance, we can already come up with naive ways to recommend, make recommender systems, to group data. As soon as we have distance, a norm for vectors, there's a lot that you can start to do. Let's go ahead and let's call it a day here. So I'm going to stop the recording. And we will, in the next video that we record, we will program a recommender system based off of only using distance.